Hey, welcome back to my another tutorial. So this part will be about ResNets. As before, to save my time and your time, I already made this tutorial. I coded it all, and so during this tutorial I'll scroll through it and explain everything to you, and some theory side, some practical side, and so on. And of course I'll upload this to GitHub, to my page and everywhere else, and you could read it, try it by yourself, and so on. And I think after this tutorial I will start object detection. This will be my last classification tutorial, at least for now. Maybe in the future I will have something more, but for now it will be last, and I'll start doing more step-by-step object detection because, well, that's on top right now. So now we'll learn how to build very deep convolutional networks using ResNets. So this model was winner of ImageNet challenge in 2015. The fundamental breakthrough with ResNet was it allowed us to train extremely deep neural networks with over 150 layers successfully. So prior to ResNet, training very deep neural networks was difficult due to the problem of vanishing gradients. However, increasing network depth does not work by simply stacking layers together. Deep networks are hard to train because of the vanishing gradients problem. As the gradients is back-propagated to earlier layers, repeated multiplication might make the gradients extremely small. As a result, the network goes deeper, its performance gets saturated, or even start degrading rapidly. So in this assignment, we will implement the basic building block of ResNets. There will be a few of them, and put together these building blocks to implement and train a state-of-the-art neural networks for image classification. So as before, I already have an imports. I'll import them. I'll use my 0 GPU. And next, as before, I defined my rows, columns, channels, and classes. I'll use same dataset of cats and dogs. So if you are interested, you can use whatever classes you want, how many you want. Maybe 10, 11, or 2, or it's your choice. But if you change classes, you'll need to change this prepare data functions. So here, okay, let's move on and run this following code to check what it will be my data set and learn about its shapes. Right now it's loading the memory, so as it loads, I'll print out the shapes so you could check it out. And we'll start moving to residual networks building. So actually, here it is, the shapes. So as before, I have 6,000 of training examples and 1,000 of test examples. So yeah, everything is quite understandable here if you watch my previous tutorials. And first part will be building a residual network. Well, it might be a second part, doesn't matter. In ResNets, a shortcut or a skip connection allows the gradient to be directly backpropagated to aerial layers. So you can here see the skip connection. So the image on the left shows the main path through the network, and the image on the right adds a shortcut to the main path. By stacking these ResNet blocks on top of each other, so you can form a very deep network. So ResNet blocks with the shortcut also makes it very easy for one of the blocks to learn an identity function. This means that you can stack on additional ResNet blocks with the little risk of harming training set performance. Well, there is also some evidence that the ease of learning an identity function even more than skip connection, helping with vanishing gradients. So accounts for ResNets can give us a remarkable performance. So two main types of blocks are used in ResNets, depending mainly on whether the input-output dimensions are same or different. So we are going to implement both of them. So why do we skip the connections and why it works? So first, they mitigate the problem of vanishing gradients by allowing this alternate shortcut path for a gradient to flow through. And second, they allow the model to learn an identity function, which ensures that the higher layer will perform at least as good as the lower layer and not worse. So At first, we'll build an identity block, and it is the standard block used in ResNets and corresponds to the case where the input activation, we say A1, has the same dimension as the output activation. For example, say A2. Keep in mind we skipped A1. So to flesh out the different steps of what happens in our ResNets identity block. So we'll actually implement a slightly more powerful version of this identity block, in which the skip connection will skip for us over 3 hidden layers rather than 2. As you can see, here is 1, 2, and 3 layers. The upper path is the shortcut path, the lower path is the main path. In this diagram, we have also made explicit the con2D and ReLU steps in each layer. So, well, it's kind of understandable, and this is needed so our output shapes would be the same as input. So, not talking a lot, we can just skip the code, and here will be my function, as here is my arguments. So as argument, first of all, there will be an x. That's understandable, that's my image. F will be integer, so this f will specify the convolutional layers middle. And filters, what filters we'll use, you'll see, of course, in code we have them here. And we'll use stage and block. Well, actually, this is to easier track our content and the names, of course, because all convolutional layers are not even convolutional should and must have different names. So I have here one convolution, second convolution, and third convolution, as it writes here. So this is 1, 2, and 3, and as you can see here, we do the adding activation. Adding, and after this we're doing activation ReLU. So let's just build this, and here we have an example, and we can also run this. I made a example, for example, float with these placeholders, and made on random numbers. And here we push we call our identity block with such parameters and so on. Well, actually, it doesn't matter. We simply check if our code works with this command. And yes, it works, as you can see. Well, at least I can run it again, and it will give me different numbers because of random and so on. And well, actually, we checked our identity block works. Next, we can move to our convolutional block. I think I made a mistake here. Yeah, I made a mistake in pictures, but doesn't matter for us right now. I'll fix it in my web tutorial. Actually, here shouldn't be any convolutional layers because we are not, as you can see, we are not doing anything with it. There's only this path and adding and ReLU. So next we are moving to convolutional layer. And actually, before we implement the ResNet identity block, now will be convolutional block, and in the other type, this is the other type of the block. You can use this type of block when the input and output dimensions don't match up. So the difference with the identity block is that there is a con2D layer in the shortcut path. Keep in mind, before there shouldn't be this path. So convolutional 2D layer is the shortcut path is used to resize the input x to a different dimension so that dimensions match up in the final addition needed to add the shortcut value back to the main path. For example, to reduce the activation dimensions height and width by factor of 2, we can use a 1x1 convolutional with a stride of 2. The con2D layer on the shortcut path does not use any non-linear activation function. Its main role is to just apply a learned linear function that reduces the dimension of the input so that dimensions match up for the later addition step. So actually we can move again up to the code and we'll test it up. And as you can see now, here we have actually the same code as it was before. And now we added a shortcut path. It is here, and we have two ways here. So actually we can build this and test it out if it works for us. It gives us zeros and so on. Let's run it again and we'll see it. Well, it changes, so it's not a problem if there is a zeros, because there is uniform initialization, but it doesn't matter for you right now. If you want, you can change the initialization function and Google it on internet, what possible functions you can use and so on. But lastly, the main path of this tutorial is this function. See, so we now have the necessary blocks to build a very deep ResNet, and in this figure describes in detail the architecture of this neural network ID block. In the diagram, it stands for identity block, and ID block X3 means you should stack 3 identity blocks together. So also, again, I'm not getting into details. I wrote it here in details. What is every stage? For example, here we do a zero pad, we do a convolutional layer, and then we do again convolutional block, and then we use identity blocks of skip connections and so on. So actually, and here we get an output, and this way we get the 50 layers deep of our convolutional network. So anyway, we will implement the ResNet with 50 layers, describe it in this picture, in this figure, and our architecture will be following, and we'll do a convolutional 2D, batch norm, ReLU, max pooler, convolutional block, and then we'll call our ID block, convolutional block, ID block 3, convolutional block, ID block 5, and so on. And right now, arguments will be slightly different. So here will be our input shape and classes. So as default, I made this here, and classes as 2. As I said, you can change it, you can test different parameters, because if I would change this, for example, to 200 by 200 and by 3, my results will be better, but my training would take much more time. So just for this tutorial, I'll do as it is with this size of images. And as you can see, here is identity blocks, and with such big quantities of filters and so on. And actually, you can play around with it and test everything. You can even try to add more layers if you want. It's up to you. And I'll just build this and run the following code to build models graph. Okay, it's building the graph. I hope so, and I hope there won't be any errors. So then we compile our model. I'll use Adam optimizer and loss categorical cross entropy. And now our model should be ready to be trained. And we'll run this simple line of code, xtrain and ytrain as input. Epoch I'll use 100 and batch size of 64. If you are trying to play around this with CPU, it might take quite some time for you. And even it might be not possible to use 64. Try it lower and test it out for you. You can even try not that much of epochs, but as I'm using this on my GPU, it's not a problem for me to train it, and it will take for me about 15 minutes. I don't know if there won't be any errors. I hope not, and we'll see. It's starting, I hope, and in a moment it should begin. Epoch first from 100, And yeah, as you can see, it started training, and here's my accuracy and loss. And yeah, actually I'll wait for 100 steps, and simply right now I'll pause the video and I'll come back when our training will finish, and we'll see what results I'll receive. So it actually finished training just right now, and as you can see, my accuracy reached about 99% and loss was about 0.02 or 1 or 3 or doesn't matter, it's average. So now let's check what is our performance on our test data set. It's running, and test accuracy is 72%. It's quite accurate, I could say, because, well, actually we could increase it a little more if we train it a little longer or we use another initialization step. But actually, to get better accuracy, we would need to use ResNet of 100 layer, 150 layer, higher picture image, input image, and so on, so that our model could train it better. But then the size, I don't know, grows exponentially and the training time is very long. So that's nice. Actually, it's much better than it was before, and well, it's still hard to say what if it predicts it accurately, but we have what we have. Anyway, let's move forward. We can print our model summary, and well, actually let's do this, and you could see that it has a lot of deep layers, and it has total parameters, trainable parameters, and not trainable parameters, just like this. That's a lot, I could say. And next, for future use, we can save our model. For example, if you run this, but our model takes a quarter of gigabyte, so I won't save it and I won't use it in future. So anyway, I will skip this. It's something similar is to use model load if you want, but finally we can run the code below to visualize our ResNet, and if you want we can do this, but this will be very long graph. Okay, plot model is not defined, so well, I need to import it, I think, but I don't remember what actually from Keras utils, something like, okay, I'll import it from Keras utils import plot model, I think. From Keras, here should be a dot, pull this, and let's see. SVG is not imported. Okay, let's move up. Let's import from Python display. We'll import SVG. I hope something like this it should be. Let's build again. Model to dot. Okay, one more. I hope one more. From Keras utils visualize utils import model to dot. Plot it, and as you can see, it's very big image. And here is, for example, our model where we created a shortcut path in the right and the longest path on the left, and we have them, I don't know, a lot of them, and in total we have 50 layers and so on. So it actually doesn't matter a lot, and you can save it as image if you want, or yeah, it's already saved as image, and you can check this out. And what you should remember from this short tutorial, so very deep plain networks don't work in practice because they are hard to train due to vanishing gradients, as we used to do in all our previous tutorials. The skip connection helped to address the vanishing gradient problem. They also make it easy for ResNet block to learn an identity function. So there are two main types of blocks, the identity block and convolutional block, as we implemented in our tutorial. And very deep ResNet networks are built by staking these blocks together, as you saw. And you can test it out if you want to stake more of these and to get better results, but I won't waste my time and I'll move to object detection. I'll say that ResNet is a powerful backbone module that is used very frequently in many computer vision tasks. ResNet uses skip connections to add the output from an earlier layer to a later layer. This helps it to mitigate the vanishing gradient problems. And of course, you can use Keras to load the pre-trained ResNet 50 or use the code I have shared and I will share with you in this tutorial. Anyway, this was a great tutorial and I didn't want it to make it long with few videos and so on. So because it doesn't matter a lot and I wanted to share with you it and experience and knowledge I get when I implemented it. And anyway, thank you all for watching. This was a great tutorial. Good luck and see you in the next video. By the way, subscribe and like my video. Thank you.